All right, so in this video, we're going to talk about definite integrals, and we've already seen in past sections that an integral setup might look something like this, where we have our integral symbol, the function that we're integrating, and then this tells us the variable that we are integrating with respect to. Now, this is called an indefinite integral. So an indefinite integral. For a definite integral, we're now going to have kind of a similar setup here, but we're going to have this a and this b. Okay, so this is a definite integral. Anytime you have the a and the b right there, it tells us, gives us an interval on which we're actually integrating. And so the thing to remember also is because of this dx right here, telling us with which variable we're with respect to, that these a's and b's are also x values. Okay, so that's an interval on the x-axis on which we're going to integrate. And we also know that from the past, this whole integral idea gives us this area under the curve. So if this is our function f of x, this is the area that we would find on the interval from a to b by computing this definite integral. Now there's going to be much more about area to follow, but for now just remember, if it doesn't have the bounds on it, it's an indefinite integral. If it has the bounds, the a and the b, constants, it's going to be a definite integral. Okay? So to compute a definite integral, we really don't do anything through the integration that's different until the end. So just kind of ignore the 0 and the 5 for now, and let's integrate this as we usually would. And so for integrals, we know we add 1 and divide. So here we would get our 5x minus 1/2 x squared. Remember, an integral and an antiderivative are the same thing in the sense that if I now take the derivative of this, I should end up with that. Okay? Now, all's well and good. I can't forget my plus c either, and I'm going to have to circle back and talk about that here in a minute. But when we have now a definite integral, I'm going to say I'm evaluating from 0 to 5. And so what I'm going to do is I am going to take this guy here, evaluated at 5, minus this thing here, evaluated at 0. So I take my 5, and I plug it in every place I see an x, and then minus that same thing now evaluated at 0. All right, now the reason we do that, we will talk about a little later when we get into the fundamental theorem of calculus, but for now, just remember, integrate as usual, and then when you evaluate, it's that top number plugged in minus the bottom number plugged in. Now, a couple things, a little bit of number crunching here, and we'll get to that, but a couple things here first. This plus c, right? We added the plus c as we always should for indefinite integrals. But for definite integrals, because of how we evaluate by the top number minus the bottom number, we're going to have this plus c minus c every single time. Every single time. So for definite integrals, those c's will always subtract off to 0. So for a definite, and hear me very carefully here, for a definite integral, the plus c isn't a big deal if you don't write it for me, but for an indefinite, you would always have to have that, okay? So then we would just compute these numbers, a little bit of number crunching there, and we end up with 25 over 2. And that is a really good thing, right? Because this is actually the problem we did with the Riemann sum a couple videos ago, and we still came up with that 25 over 2. Now you're seeing the shortcut applied and how much easier and more efficient it actually is. Okay? Now, I also want to take a look at this a third way, and that is by graphing it. Remember how I said it's the area under the curve on the interval? Well, our function 5 minus x is just a line. It's a line that has an x-intercept at 5 and also a y-intercept at 5. So here's our function, y equals f of x. This is at 5, and this is also at 5. And we're being told to compute the area on the interval 0 to 5, so the actual area that I want is this guy right here. Well, that's just a triangle. We know that a triangle, the area formula is 1/2 base times height. And our base in this case, is going to be 5. Our height is going to be 5. So we've got a base of 5 and a height of 5, which gives us that 25 over 2, now a third way of computing the area. So originally we looked at this with a Riemann sum, kind of messy, but we got there using our summations and our limits. Then we used the definite integral and got the same answer, much more efficient. And then we also used some just basic elementary geometry and we're able to compute this. Now obviously most functions that we talk about aren't going to be able to be done as I've done there in blue, but it's still a nice method to just kind of remind you what we're doing here. Okay, so for the next example then, we've got another definite integral from -2 to 1, and the function's negative x squared minus 2, followed by our dx. So when it comes to integrating this, again, the first part's always the same, just integrate as usual, and then we'll evaluate at the end. So this will be a -1/3 x cubed minus 2x. I don't need to put the plus c there because we know that it would go off to 0 if I did write it. You certainly can, but for a definite integral, if you don't write the plus c, it's totally fine. So we'll evaluate now, where I take the 1 and plug it in first, and then minus the function evaluated at the bottom number, which is -2. So I've plugged the 1 in to start, and then minus, and we'll plug the -2 in for that last part. And when we simplify this down, this gives us a -9 for the final answer. Now, you might be asking yourself, well, you said just a minute ago it gives us area under the curve. And it does, but we've got this negative here. So what's happening? Well, it's actually pretty interesting because if we're just computing an integral, you can get a negative number. That's perfectly reasonable. Interpreting it, though, is where you'll really benefit from seeing the graph. We know that this is just a parabola. It opens down, shifted 2 units down. So we've got something that looks like this. And if we're interested in the interval -2 to 1, well, -2 would be maybe right here, and 1 would be right here. Notice what's happening. That -9 is giving us the area below the x-axis, hence the negative. So you want to read the instructions carefully when it comes to these integrals. If they truly want area, which we'll get to much more heavily later in the chapter, then you'll always get a positive number. But if they're just wanting you to evaluate or maybe evaluate and then interpret, the negative is perfectly reasonable in the fact that it would just be below the x-axis.